Have you ever caught yourself staring into the dark and wondering, what happens if a nuclear bomb goes off in space? In the vacuum out there, there's no air to shove, no shockwave to thunder across a city. So, would it be just a silent flash, a camera strobe against an endless night? Or would it birth phenomena we never witness on Earth, the kind that shrug off our intuition and rewrite the rules we learned under blue skies? Let's walk this slowly, like a midnight conversation where the clock has stopped ticking. To answer that question, we'll begin at the core, what a nuclear explosion actually is. Two families run the show. One tears heavy atoms apart, fission, urging a uranium or plutonium nucleus to drink a neutron and split into lighter fragments, shedding mass that reappears as energy. The other presses the lightest atoms together, fusion, coaxing hydrogen into helium under ferocious heat and pressure, the way the sun has been quietly doing since before language learned our names. Both convert a pinch of mass into a storm of energy. The difference is temperament. Fission is a domino hall set ablaze. Fusion is a star's heartbeat trapped in a bottle. On Earth, we learned these temperaments the hard way. The fission bomb, an atomic device, relies on a chain reaction. Fast neutrons from one split crash into neighbours, multiplying the splits until, in a blink, the stockpile of potential turns to light, heat, blast. Fusion devices, hydrogen bombs, stack stages. A fission spark plug compresses fuel like deuterium and tritium to star-like conditions, and the fusion surge answers with orders of magnitude more energy for the same mass. For scale, if TNT is a firecracker, Hiroshima was a thunderclap, and Tsar Bomba was a mountain collapsing in light. Yet even that colossus is a spark compared to the sun, which every second turns millions of tons of itself into radiance without so much as a raised voice. But that's Earth thinking, air, pressure, weather, the comforting presence of a medium that carries shock and builds clouds. Take away the air and the script changes. In space there is no mushroom, no blast front galloping through neighbourhoods, no roar, sound has nowhere to ride. What remains is the purest part of any nuclear event, a brief, blinding sphere of plasma and a flood of radiation racing outward at light speed, unbothered by wind or wall. It is, unsettlingly, a quiet catastrophe. And here's the twist that pulls our thought experiment out of the realm of what if. More than half a century ago, humanity did it once. We detonated a nuclear device high above the Pacific, beyond the thick of the air. The night sky bloomed with unnatural auroras, electronics far away hiccuped and failed. Satellites suffered for months as an invisible belt of radiation wrapped the planet like a hostile gift. We'll get there. First, we need the basics pinned down, the physics that rule on Earth and the rules that unravel in vacuum so that when we step back into space, we can understand what we're actually seeing. So, what is a nuclear explosion made of, piece by piece? How does atmosphere turn light into blast and blast into ruin? And when the air disappears, why does the flash stay while the roar dies? Keep your voice down and your curiosity up. We start at the atom, then climb, to the stratosphere, to the quiet above it, and finally to places where gravity bends even light into obedience. So let's get our hands dirty with the physics. What exactly is a nuclear explosion? Strip away the imagery of mushroom clouds and apocalyptic fire, and what you have is really a story of atoms choosing violence in two very different ways. Fission and fusion. Fission first. Picture a bowling alley, but the pins are uranium nuclei and the bowling balls are neutrons. One strike, and instead of just scattering the pins, each shattered pin spits out new bowling balls, rolling into other lanes, smashing more pins, releasing more balls, until the whole alley is chaos. That's a chain reaction. The trick is to line up enough uranium or plutonium, tightly packed, so the neutrons don't escape before they've done their destructive duty. When it works, the release is instant, staggering, and final. Fusion is the opposite temperament. Instead of tearing apart the heavyweights, you squeeze the lightest kids on the atomic playground, hydrogen nuclei so tightly that they merge into helium. But these little particles don't want to get close. Their electric repulsion is like trying to press two strong magnets together the wrong way. Only under pressures and temperatures similar to the sun's heart, millions of degrees, will they relent. And when they do, The energy unleashed makes fission look like a starter pistol before a cannon. This is why fusion is nature's favourite. Every second, the sun takes about 600 million tons of hydrogen, welds it into helium, and casually converts about 4 million tons of that mass into pure energy. Think about that. 4 million tons of matter vanish into light and heat, every second, every day for billions of years. No fuel rods, no mushroom clouds, just a cosmic bonfire. But humans, not content with sunlight, decided to make their own sun in a bottle. The hydrogen bomb uses a fission blast as a match to ignite the fusion stage, compressing deuterium and tritium into star-like conditions. The yield leaps by factors of hundreds or thousands. The Soviet Tsar bomber of 1961, the most powerful nuclear device ever detonated, was essentially a man-made sunrise that lasted a fraction of a second. Its energy was about 1,000 times greater than Hiroshima's. Here's the kicker. Even that mountain of fire barely scratches cosmic scales. The sun produces the equivalent of tens of millions of Tsar bombers every single second. It makes our most terrifying weapons look like damp firecrackers by comparison. So nuclear explosions, whether human-built or stellar, come in two flavours: fission's domino collapse and fusion's star-making squeeze. And understanding those is our entry ticket before we can talk about how they behave differently on Earth, and how they turn bizarre when unleashed into the silence of space. Let's stay with fission for a moment, the darker, more familiar of the two. This is the principle behind Hiroshima and Nagasaki, the reason mushroom clouds became burned into human memory. At its core, fission is just a neutron walking into the wrong neighbourhood. A heavy nucleus like uranium-235 or plutonium-239 swallows that neutron, becomes unstable, and splits in two. In the act, it spits out more neutrons, plus an enormous amount of energy. Each of those freed neutrons finds another heavy nucleus, and the dominoes tumble faster than human senses can register. The key word here is critical mass, the minimum amount of fissile material needed for this chain reaction to run away instead of fizzling out. Stack too little uranium together, and neutrons leak away harmlessly. Pack enough into a tight space, and you get a self-feeding avalanche where each split breeds more splits until, boom, the whole thing empties its energy in microseconds. Think of it this way. You're in a crowded theatre where one person panics and screams fire. If the room is half empty, maybe nothing happens. If the room is jam-packed, panic ricochets from person to person until the crowd stampedes. That's fission in social form, except instead of chaos and bruises, you get a fireball hotter than the sun's surface. When the Manhattan Project scientists assembled the first bomb cores, they weren't just working with physics, they were gambling with the geometry of neutrons. They used clever tricks like explosive lenses to squeeze subcritical pieces together in an instant, ensuring the dominoes all toppled at once instead of hesitating. A poorly timed reaction would simply fizzle, wasting precious plutonium. A well-timed one would flatten a city. That's why Hiroshima's bomb, Little Boy, was relatively crude but devastating. Uranium slugs smashed together to go critical in a fraction of a second. Nagasaki's Fat Man was more sophisticated, using implosion to compress plutonium into its unstable sweet spot. Both deliver the same brutal lesson. Once you reach critical mass, nature takes over, and the chain reaction doesn't politely stop until it has burned through its fuel. It's a domino line you cannot pause, a theatre stampede you cannot calm, an avalanche you cannot outrun. Humanity learned that in 1945, and the shadow of that knowledge hasn't lifted since. Now, fusion. If fission is the domino collapse, fusion is the cosmic embrace. It's the reason the stars shine, the reason you and I exist, the reason there's enough oxygen in your lungs to even hear this whispered midnight story. Fusion is simple to describe but brutal to achieve. Take two hydrogen nuclei, just protons really, and push them so close that their mutual hatred for each other's positive charge is overcome. Suddenly they merge into helium, and the tiny missing sliver of mass reappears as energy. E just mc2, Einstein's little note on the margin, cashes out big here. But here's the catch. Under normal Earth conditions, hydrogen atoms repel each other like stubborn siblings refusing to share a seat. You need temperatures of tens of millions of degrees and pressures strong enough to crush mountains flat. In other words, you need a star. That's why our sun burns like a steady nuclear engine. Every second, hundreds of millions of tons of hydrogen vanish into helium, and a small fraction of that mass becomes light and warmth. To us it feels like a constant benign presence in the sky. But if you could listen to it in the language of energy, it's the most thunderous detonation imaginable, repeated endlessly, calmly, for billions of years. When humans sought to replicate this process, they ran into a cruel irony. To start fusion, you need fission. The hydrogen bomb isn't a single device, it's a duet. A fission bomb goes off first, acting like a trigger, providing the heat and pressure necessary to squeeze hydrogen isotopes like deuterium and tritium into fusion. What follows is a chain of reactions so violent that it makes ordinary fission weapons look antique. The hydrogen bomb is humanity's clumsy attempt at building a star in a box, and in October 1961, the Soviet Union lit the fuse on the largest one ever made, Tsar Bomba. Its yield was so monstrous, about 50 megatons, that it broke windows nearly 1,000 kilometers away and rattled the planet's atmosphere. To put that into perspective, Hiroshima was 15 kilotons. Tsar Bomba was over 3,000 times stronger. A single weapon with the power to erase a metropolitan region in a second. But even Tsar Bomba, humanity's loudest firecracker, is laughable compared to nature. The sun pumps out the equivalent of tens of millions of Tsar Bombas per second. That's the scale we're talking about. Our deadliest inventions are nothing more than sparks in the forge of the cosmos. Fusion is, paradoxically, both our greatest terror and our greatest hope. Terror, because it birthed the hydrogen bomb. Hope, because if we ever tame it in reactors, it could light our cities for millennia without choking the earth. In the sun, it is creation. In our hands, so far, it has been destruction. And with that, fission and fusion in mind, we can finally measure the true weight of nuclear energy before we ask, what happens when you let it loose? Not in cities, not on battlefields, but in the silence above the atmosphere. Before we hurl our bomb into orbit, let's pause for scale, because numbers this large only mean something if you anchor them to everyday life. Start small. 1 ton of TNT, our yardstick for explosions, releases about 4 billion joules of energy. That's enough to boil roughly 300,000 kettles of water. Now multiply that by 1,000 and you get a kiloton. Hiroshima's bomb? About 15 kilotons, 15,000 tons of TNT. Imagine an entire freight train of dynamite stretching further than the eye can see, all lit at once. That was Hiroshima in a single flash. Fast forward to 1961 when the Soviets decided to build something so absurdly large that even the generals flinched. Tsar Bomba, 50 megatons. That's 50 million tons of TNT, equivalent to detonating every firework humanity has ever made, every stick of dynamite, every hand grenade, and then multiplying the result several times over. Its shockwaves circled the Earth 3 times. And yet, here's the humiliating part. Compared to the cosmos, it was a sparkler. The sun converts about 4 million tons of matter into energy every second. That's like dropping one Tsar Bomba after another millions of times per heartbeat. It makes our doomsday weapons look like wet matches, but the comparison is useful, because when people talk about nukes in terms of megatons, the numbers blur into abstraction. Tsar Bomba could have vaporized Manhattan, erased Paris, or turned London into a smoking crater. But the sun could do all of that, to every city on Earth simultaneously, and not even notice. This matters, because the physics is the same. Fission and fusion aren't human inventions, they're natural processes. We just hijacked them. When we built bombs, we weren't creating new laws of nature. We were copying the universe's homework clumsily and writing it down in crude handwriting. So here's the scale. Fission is terrifying, fusion is monstrous, and the sun makes both look like toys. Keep that hierarchy in mind as we shift from raw physics into lived experience. What happens when one of these explosions actually occurs on Earth, in the thick of our atmosphere? Because only then can we strip away the atmosphere and see how alien the same explosion becomes in the void. So, what actually happens when a nuclear weapon detonates here, in our atmosphere, where air itself becomes both canvas and accomplice? 3 killers step forward: heat, blast, and radiation. They arrive in sequence, like acts of a grotesque play, each one worse than the last. First comes the thermal pulse. In the first millionth of a second, the bomb creates a fireball hotter than the surface of the sun, millions of degrees. That fireball lights up the sky brighter than daylight, even if you're dozens of kilometers away. At Hiroshima, people standing miles from ground zero saw their shadows permanently etched into stone, burned into walls as the intense flash seared surfaces clean. Skin caught in direct view, blistered or ignited instantly. Within 2 kilometers of the hypercenter, almost everything combustible burst into flame. Cities don't just get flattened by nukes, they catch fire like kindling in a furnace. Next is the blast wave. The fireball swells, superheating the air around it. That air expands violently, shoving outward at supersonic speeds. This is the thunderclap we imagine when we think of nuclear bombs. The pressure front that knocks buildings off their foundations and hurls people like rag dolls. In Hiroshima, most wooden houses were shredded within 3 kilometers. Reinforced concrete fared only slightly better. The shockwave doesn't just push once, it sucks back. After the outward surge, air collapses inward to fill the vacuum, dragging debris and flames back toward ground zero. Survivors describe this as a wind that came from everywhere at once. Then comes the radiation. Visible, insidious, it travels in 2 phases. First, the initial burst, gamma rays and neutrons, delivered in the first seconds, ripping through tissue, shredding DNA, damaging bone marrow. Then the fallout, radioactive fragments lofted into the mushroom cloud, which drift down like poisoned snow. In Hiroshima and Nagasaki, some victims who survived the blast and heat later succumbed to radiation sickness, hair loss, bleeding, relentless vomiting. For many, cancers emerged years later, delayed shadows of a moment's exposure. Together, these 3 forces, heat, blast, radiation, make nuclear weapons unique. Conventional bombs kill by shrapnel or fire. Nukes kill by rewriting the environment itself. The air becomes a furnace, the pressure becomes a hammer, the soil and dust become toxic for decades. It is destruction not just of lives, but of the conditions for life. And yet, the iconic image most people picture when they hear nuclear bomb isn't seared shadows or shattered houses. It's the vast, rising mushroom cloud, and that deserves its own story. The mushroom cloud, the grim totem of the nuclear age. It looks almost artistic, sculpted, as if nature itself decided to paint a warning in the sky. But its elegance is born of brutal physics. Here's how it happens. The initial fireball, hotter than the sun's surface, superheats the surrounding air until it glows and expands violently. That bubble of plasma rockets upward, pulling with it dirt, dust, and debris. As it climbs, cooler air from below rushes in to replace it, forming a rising column, a stalk. At the top, the fireball slows, spreads outward, and mushrooms into the familiar cap. It's a cosmic lava lamp, except this lamp carries death. The size alone is staggering. In Hiroshima, the mushroom reached nearly 12 kilometers high, higher than Mount Everest. In Tsar Bomba's test, the cloud shot up more than 60 kilometers, brushing the edge of space. Imagine a thunderstorm, then multiply its violence until it breaks the sky. That's a mushroom cloud. And it's not just theatre. Inside that beautiful horror, particles of vaporized soil, building material, and bomb casing mix with radioactive isotopes. Strontium, cesium, iodine. As the cloud billows, those particles condense, clump, and eventually fall back to Earth. Fallout. Invisible killers tucked into raindrops or dust, settling on farmland, seeping into rivers, entering bones and bloodstreams for generations. The mushroom cloud is so iconic that it's become shorthand for annihilation. But remember, it only exists because of atmosphere. Without air, without convection, there's no mushroom. Take the bomb into space, and the stalk, the cap, the ominous tower of smoke, all of it disappears. What remains is raw light and radiation unshaped by air. On Earth, though, the mushroom is both spectacle and signal, a sign that beneath it, the world has been altered forever. It is physics made visible, chemistry made catastrophic, and psychology made permanent. Once you've seen one, even in a photograph, you cannot mistake it for anything else. But the mushroom is only one part of the nuclear signature. There is another, stranger child of the bomb, less visible but just as dangerous. The invisible lightning bolt, the killer of circuits, the ghost in the wires, the electromagnetic pulse. Now we step into the invisible. If the mushroom cloud is the symbol of nuclear terror, the electromagnetic pulse, EMP, is its ghost. It doesn't burn skin or topple buildings, it burns wires, topples systems. Here's how it works. When a nuclear device detonates, especially at altitude, it unleashes a torrent of gamma rays. These rays slam into the atmosphere, particularly into oxygen and nitrogen molecules, and in the process they kick loose electrons at near light speed. Those electrons cascade downward, bending and twisting along Earth's magnetic field, and the result is a sudden blistering surge of electromagnetic energy, a pulse that radiates outward faster than any shockwave. Engineers break it into 3 flavors. E1, the first jolt, a nanosecond spike strong enough to fry microchips, melting the delicate nerves of modern electronics. E2, slower, more like the effect of a lightning strike, but coming everywhere at once. E3, the long tail, akin to a geomagnetic storm, disrupting power grids, coaxing massive currents into wires stretched across countries. Think of it this way. A single nuclear blast can create an invisible thunderstorm that rains fire on circuits instead of people. And unlike blast waves, EMP doesn't care about distance in the same way. The 1962 Starfish Prime test, our one real attempt at a space nuke, knocked out streetlights and fried phone lines in Hawaii, nearly 1,500 kilometers away. Imagine sitting in your kitchen, miles from the detonation, and your radio simply dies. Not a sound, not a flash, just silence and darkness. What makes EMP especially eerie is that it rides on our own progress. Hiroshima in 1945 had no smartphones, no satellites, no internet. But today, a single high-altitude detonation over a continent could cripple power grids, knock out GPS, silence communications and unravel economies in minutes. It is a weapon tuned not to bodies, but to civilizations. And yet, like the mushroom cloud, it depends on air. The gamma rays need atmosphere to shake electrons loose, to whip them into a frenzy. In space, the EMP doesn't vanish entirely, but it changes character. There is no air to stir, no long cascade of ionized particles, which means the rules of destruction, blast, mushroom, EMP, start to fray as we leave the atmosphere, and that is our pivot point. We've seen what nukes do on Earth, where the air itself becomes an accomplice. But now imagine the same bomb detonated where there is no air, no weather, no sound, only vacuum. What happens to the fireball, the flash, the pulse, the fallout? That's where we're headed next. So let's take the air away. Strip the stage bare. No atmosphere, no winds, no weather. Just the cold vacuum of space. Now drop a nuclear bomb into that silence and light the fuse. What happens? The first thing to know, no blast wave. On Earth, the fireball swells against the surrounding air, compressing it into a shock front that tears buildings apart. In space, there's no air to shove. The bomb still releases the same titanic energy, but there's nothing to carry the punch. No walls collapse, no windows rattle. In fact, if you were floating nearby in a suit, which, let's be honest, you wouldn't survive for other reasons, you'd see the detonation but hear nothing. Silence. The fireball still forms, but only for a breath. It expands furiously, a ball of plasma tens of millions of degrees hot, but because there's no air to hold the heat, it cools almost instantly. No mushroom cloud rises, there's no convection to sculpt one. The iconic Tower of Destruction belongs solely to Earth. In space, you get a brief, furious sphere of light that fades before you can blink. But don't be fooled by the quiet. The bomb's energy is still there, it just travels differently. Instead of blast and heat carried by atmosphere, the energy leaves as radiation and light. Gamma rays, X-rays, ultraviolet, visible light, infrared. All of it races outward in straight lines, unchallenged, until it strikes something. That something could be a satellite, a space station, or an unlucky astronaut. From a distance, the detonation would look like a flashbulb going off. An intense white glare against the black canvas of space, then gone. No smoke, no lingering flame, no rolling thunder, just a ghostly camera flash fading into silence. Astronauts aboard the ISS, if they happen to be looking, might see a sky that blinks and then returns to normal, as though the universe itself had taken a photograph. And yet, that's only the beginning. Because without air to absorb or scatter them, those high-energy photons and particles travel much farther than they do on Earth. Instead of being confined to ground zero, they can sweep across hundreds or thousands of kilometers, striking electronics, stripping atmospheres, even sparking auroras if Earth's magnetic field gets involved. A nuclear detonation in space is less like an explosion in a city, and more like dropping a stone into a still pond. The ripples spread far wider than you expect, but in forms our Earth-trained instincts don't recognize: quiet, bright, short, and profoundly dangerous. Here's the unsettling part. Silence in space doesn't mean safety. Strip away the blast wave and the mushroom cloud, and what you're left with is the pure radiation, unfiltered and undiluted. On Earth, air absorbs, scatters, and slows much of that fury. In vacuum, nothing stands in its way. Picture it. A bomb goes off 400 kilometers above Earth. No roar, no shock, but gamma rays and X-rays blaze outward like invisible spears. Neutrons too, fast, brutal, unshielded, racing in straight lines until they strike something solid. Satellites suddenly lose their sight, solar panels sputter, delicate circuits fry. An astronaut drifting a few hundred kilometers away would never hear a thing, but their body would be riddled by radiation in the blink of an eye. This is the paradox. Space nukes are quieter, but their reach is longer. On Earth, devastation is confined to a radius of a few kilometers. In orbit, the same detonation could cripple spacecraft spread across continents' worth of sky. It's less about craters, more about silencing machines. And because space doesn't slow particles down, the fallout looks different too. There's no dust cloud to rain radioactive ash on farms. Instead, charged particles from the blast can become trapped in Earth's magnetic field. Once caught, they spiral around the planet, forming artificial radiation belts, deadly invisible rings that hang around for months. In 1962, one such test damaged or destroyed several satellites that had only just been launched. It was as if humanity had poisoned its own backyard before even unpacking the furniture. Think of radiation in this context as a spotlight with no lampshade. On Earth, the shade, our air, dims it, shapes it, turns it into blast, heat, and fallout. In space, the shade is gone. The bulb burns naked, shining in every direction, and anything within line of sight gets scorched. So yes, the silence of space makes the detonation seem almost anticlimactic. But the truth is crueler. The real danger is invisible, silent, and far-reaching. A bomb in orbit doesn't blow things over. It haunts them, quietly, relentlessly, with rays and particles that travel further than any shockwave ever could. Now, let's talk about the phantom menace of a space nuke, the EMP, electromagnetic pulse. On Earth, EMP is born when gamma rays smash into air molecules, hurling electrons loose, and Earth's magnetic field twists those electrons into a storm. But out in space, with no atmosphere to play with, the rules change. In the vacuum itself, there's no air for gamma rays to collide with, no swarm of electrons to whip up. That means the classic continent-wide blackout EMP is weaker or absent if you detonate far from any planet. A nuke into deep space is a lonely flash, bright, silent, dangerous to anything in its line of sight, but it won't turn off televisions in Tokyo. But bring Earth's magnetic field back into the picture, and things get messy. If the detonation happens in low orbit, the bomb's gamma rays still hit the thin upper layers of atmosphere. That's enough to free electrons. Those electrons, caught by the geomagnetic field, race along its invisible lines and pour energy into the ionosphere. Suddenly, power grids and radios thousands of kilometers away feel a shock from a bomb they never saw. This is exactly what happened during the Starfish Prime test in 1962. The bomb went off 400 kilometers above the Pacific, and Hawaii, nearly 500 kilometers away, lost streetlights and phone service. The detonation had essentially shaken Earth's magnetic skeleton, sending tremors into its nervous system. Imagine flicking a tuning fork. The fork itself rings, and the sound travels into the room. A space nuke near Earth is like striking the planet's magnetic fork. The vibration hums across continents, invisible but devastating. So while a nuke in deep space is mostly a flash and a radiation storm, a nuke near Earth becomes a strange hybrid. Silent, yes, but capable of toppling the electrical scaffolding of modern civilization. Not by force, but by ghostly resonance with the planet's own magnetic field. And here lies the eerie beauty. Only in a space do bombs reveal this trick. Only in the void can a flash of gamma rays reach down and make cities go dark, satellites fall dumb, and technology collapse without a single pane of glass shattered. And now, with the stage set, we can finally tell the story of the one time humanity actually did this on purpose. A nuclear detonation in space that painted auroras across the sky and broke machines on Earth. Let's set the scene. The year is 1962, deep in the Cold War. The United States and the Soviet Union are locked in their arms race, measuring power not just in bombs but in how far, how high, and how strangely they could be detonated. Testing on the ground and in the atmosphere had already filled deserts and atolls with scars. So the Americans decided to go higher, much higher. The operation was called Starfish Prime. On July 9th, just before midnight in Hawaii, a Thor missile rose from Johnston Atoll, a remote speck of land in the Pacific. Riding on top was a warhead with a yield of about 1.4 megatons, roughly 100 times the Hiroshima bomb. Its target? Not a city, not an enemy base, but a patch of empty space 400 kilometers above Earth. For context, that's about the same altitude the International Space Station orbits today. At 11 p.m. local time, the bomb went off. To people in Hawaii, 500 kilometers away, it looked as if someone had switched on the sun. The night sky flashed bright white. Shadows jumped across the streets, and the ocean glinted as if dawn had arrived in an instant. For a few seconds, Honolulu was lit like midday. But the light show didn't end there. Strange veils of colour spread across the sky. Artificial auroras, blooming in red, green, and violet. These ghostly curtains lingered for minutes, stretching across the Pacific. Some could even be seen as far as New Zealand. Imagine looking up and seeing the heavens painted with unfamiliar radioactive brushstrokes, auroras not from solar storms but from human hands. What was happening? The explosion had hurled energetic electrons into Earth's magnetic field. Those electrons spiraled along the field lines, colliding with the atmosphere at far-flung locations, making the upper air glow. In the north, Hawaii watched the show. In the south, over the opposite side of the globe, matching auroras appeared, a symmetrical echo across Earth's magnetic skeleton. For ordinary people on the ground, it was surreal, almost beautiful. But for machines, it was lethal. The beauty didn't last. While people in Hawaii marveled at the strange lights, the island's infrastructure was quietly being fried. Streetlights blinked out, telephone lines crackled and went dead. Microwaves relays, critical for communication across the Pacific, burned out. All of this, mind you, happened 1,500 kilometers from the detonation. No sound, no blast, just silence, and then darkness. This was the electromagnetic pulse flexing its muscles. Starfish Prime had created one of the largest EMP events ever recorded. Circuits that had no idea a bomb had gone off suddenly carried currents strong enough to melt them. Hawaii, with its primitive electronics by modern standards, was already rattled. Imagine what that same pulse would do today to a world knitted together by satellites, smartphones, and fragile power grids. But the real devastation was above Earth, in orbit. The high-energy particles released by the detonation didn't simply vanish. Caught by Earth's magnetic field, they spread into artificial radiation belts, deadly invisible rings that wrapped around the planet. In the months that followed, those belts quietly ate away at satellites. Telstar 1, the brand new pride of American telecommunications, the satellite that had just beamed the first live television across the Atlantic, began to glitch and stutter. Ariel 1, Britain's first satellite, failed entirely. In total, at least half a dozen spacecraft were crippled or destroyed, not by direct hits, but by radiation poisoning. Humanity had only just begun to touch space, and we'd already made it hostile to our machines. It was as if we'd salted the Earth, except this time we salted the sky. The military planners got their data. Yes, space nukes could cripple infrastructure and satellites. But they also got an unintended lesson. The fallout of a space detonation doesn't fade in hours or days. It lingers, a poisoned halo, ready to shred anything that dares to orbit through it. Starfish Prime was supposed to be a demonstration of strength. Instead, it was a demonstration of fragility, not just of cities, but of the very systems that keep modern civilization humming. And it left leaders on both sides of the Cold War with a sobering realization. If we kept detonating bombs in space, we might not only destroy each other's satellites, we might make Earth's orbit unusable at all. The fallout from Starfish Prime wasn't just physical, it was political. What had begun as an experiment quickly turned into a warning written across the sky. In Washington, the results rattled officials. The auroras were strange, yes, even mesmerizing. But the satellite failures were a gut punch. The US had just launched its first generation of communication satellites, each one a fragile jewel of Cold War prestige. To see them crippled not by enemy action but by their own country's test was a bitter irony. And Moscow was watching too. The Soviets were conducting their own high-altitude experiments, some nearly as destructive, each side trying to prove it could blind the other's eyes in the sky if war came. It didn't take long for both to realize. This wasn't sustainable. Every blast poisoned the shared playground of space. If they kept going, they wouldn't just be sabotaging each other, they'd be sabotaging themselves. That's why, only a year later, in 1963, the world took a hesitant step back from the brink. The Partial Test Ban Treaty was signed by the United States, the United Kingdom, and the Soviet Union. It banned nuclear tests in the atmosphere, underwater, and in outer space. Underground testing would continue for decades, but the sky, at least officially, was off limits. By 1967, the principle was extended further with the Outer Space Treaty. This one explicitly prohibited placing nuclear weapons in orbit or on celestial bodies, or detonating them in space. For the first time, humanity drew a red line not just on Earth, but above it. Space was to be, at least in law, free of weapons of mass destruction. Of course, the Cold War didn't suddenly become peaceful. Nuclear arsenals kept growing, missiles got faster, submarines prowled the oceans with warheads ready to launch. But one door had been closed. The lesson of Starfish Prime, that a single bomb could haunt the planet's magnetic field, cripple satellites, and scar the sky for months, was enough to persuade rivals that space nukes were a step too far. Still, the echoes of that single blast remained. Scientists who studied the artificial auroras realized they were glimpsing something uncanny. How human technology could mimic, however crudely, the power of the sun and the storms it hurls across space. And that realization carried us into the next chapter, seeing nuclear fire not just as a weapon, but as a reflection of the cosmic furnace we orbit every day. Now let's widen the frame, because if you want to understand nuclear fire in space, you have to look at the real master of the craft, the sun. Every second our star performs a miracle that makes Tsar Bomba look like a child's sparkler. At its core, temperatures soar to about 15 million degrees Celsius. Under that crushing pressure, hydrogen atoms fuse into helium, releasing energy so enormous that 4 million tons of matter vanish into pure light every second. And it's been doing this, calmly, without pause, for 4.5 billion years. What we see as gentle sunshine, the warmth on your skin, the light spilling through your window, is the residue of a perpetual nuclear explosion happening 150 million kilometers away. If the sun were a bomb, it would be the only one big enough to power life itself. But the sun doesn't always behave. Sometimes its nuclear heart hiccups. On its surface, tangled magnetic fields snap and unleash solar flares, bursts of radiation that make our biggest hydrogen bombs look like matchsticks. And sometimes those tantrums go further, ejecting coronal mass ejections, CMEs, billions of tons of plasma hurled into space, riding magnetic fields strong enough to rattle planets. We've seen what this means on Earth. In 1859, the Carrington event sent a solar storm slamming into our magnetosphere. Telegraph lines sparked, operators were shocked, and auroras flared as far south as the Caribbean. In 1989, a smaller storm blacked out Quebec for 9 hours, frying transformers with currents they were never built to handle. In other words, the sun has already shown us what a nuclear-scale event in space looks like. No mushroom cloud, no blast wave, just radiation and magnetism, invisible forces that can darken cities and paint the skies with fire. Sound familiar? It's the same lesson Starfish Prime delivered, only this time from a natural bomb that never stops ticking, and the comparison cuts both ways. When we detonated a warhead in orbit, we created artificial auroras. When the sun hurls a CME, it too lights the polar skies with shifting curtains of red and green. When our bomb poisons satellites with radiation, it was only echoing what solar storms do regularly, battering spacecraft and astronauts alike with high-energy particles. So in trying to master nuclear fire, humanity has done little more than imitate the sun, a pale reflection of the same physics that makes stars shine. Our bombs are finite, clumsy, and dangerous. The sun's furnace is eternal, stable, and life-giving. Yet both remind us of the same truth. The universe runs on explosions. But let's push past the sun. Because if stars are the natural stage for fusion, then black holes are the opposite. The stage where even light is trapped, where energy goes in but doesn't come back out. So what if you detonated a nuclear bomb near one of these cosmic monsters? First, you'd have to imagine the scene. A bomb approaches the event horizon, the invisible boundary beyond which no signal, no photon, no whisper escapes. To a distant observer, time near that edge appears to slow down. The flash of a nuclear blast wouldn't look like an instant detonation. Instead, it would stretch, drawn out, fading into a dim red glow. It's like watching an explosion in slow motion, its light smeared by gravity until it vanishes altogether. Then there's the energy itself. Normally, a nuclear detonation floods space with photons and particles, spreading destruction outward. Near a black hole, much of that radiation would be bent, pulled, or swallowed whole. Some rays would curve around the black hole, appearing to us as strange arcs or halos, a gravitational lens made of fire. Others would fall straight in, gone forever, adding their fury to the black hole's invisible mass. It's almost humiliating. The most terrifying force humanity has ever built, a nuclear bomb, wouldn't even scratch a black hole. It would be a firefly at the edge of a furnace, its light bent, stretched, and finally snuffed out. And yet, the strangeness doesn't stop there. If the bomb exploded within the swirling accretion disk of gas that surrounds many black holes, it might momentarily disrupt the flow, heating gas, twisting magnetic fields, maybe even altering the monstrous jets that some black holes spit out at near-light speeds. Compared to the scale of the black hole, it would still be trivial, but for a brief instant humanity's fire might echo in a place where stars themselves are shredded. Here, nuclear fire becomes a kind of cosmic joke. The same blast that can erase a city or blind a satellite is nothing but a flicker against the abyss. The lesson is sobering. Even our greatest violence is small compared to the engines that already rule the universe. And yet, thinking about bombs near black holes isn't wasted fantasy. It sharpens a deeper question. What happens when human technology meets the universe's extremes? Because as we'll see, scientists once dreamed not of destroying with nuclear fire, but of riding it, like a rocket engine, into the stars. Now comes one of the strangest chapters in nuclear history, when scientists ask not, how can we kill with this, but how can we travel with it? Enter Project Orion. The idea was as audacious as it sounds. Build a spaceship powered by nuclear bombs. Not one bomb, not two, but hundreds, even thousands, dropped out the back like depth charges detonating in sequence. Each explosion would slam against a giant metal plate bolted to the ship's rear, and the shock absorbers would translate that violence into steady thrust. Imagine propelling yourself across the solar system by setting off a string of thunderclaps, and you're close. It was the 1950s and early 60s, the golden age of crazy optimism. Rockets had barely touched the edge of space, but engineers at Los Alamos and beyond were sketching ships the size of skyscrapers, crewed by dozens of astronauts, each one propelled forward by the fury of nuclear fire. With Orion, Mars wasn't a dream for the next century, it was a pit stop on the way to Saturn. Some designs even suggested interstellar travel, one nuclear pulse at a time, and it wasn't just fantasy. Small-scale experiments using conventional explosives, thankfully, showed the principle worked. The metal plate wouldn't vaporize, as skeptics feared, it could actually survive repeated blasts. With each detonation, the ship would leap forward like a cosmic pogo stick, accelerating towards speeds no chemical rocket could hope to reach. The math was intoxicating. A chemical rocket needs tons of fuel just to reach orbit. An Orion craft, by contrast, could have carried thousands of tons into space. Space stations, colonies, even whole cities in a can. Science fiction writers went wild. Freeman Dyson, one of the great physicists of the era, took the project seriously enough to spend years studying it. But reality, as always, had the last word. Political reality especially. Testing Orion meant detonating real nuclear bombs in Earth's atmosphere or just above it, littering the planet with fallout before the ship even left orbit. And by the 1960s, treaties had started closing that door. The Partial Test Ban Treaty of 1963 slammed it shut. Orion never flew. Its grandest designs remained drawings in dusty archives, dreams of a spaceship that roared forward on nuclear fire. Still, the concept never entirely died. Today, when scientists talk about nuclear propulsion, fission reactors, nuclear thermal rockets, even fusion drives, they're echoing Orion's spirit, using the atom not for war but for exploration. The same fire that casts shadows over Hiroshima might, one day, carry us to the stars. But before we chase dreams of nuclear starships, let's pull back and take a cosmic breath. Because Orion's vision, riding bomb after bomb into the void, wasn't just science fiction optimism. It was a mirror held up to the universe itself. Out there, explosions aren't rare. They are the grammar of the cosmos. Stars are born in the collapse of clouds, and they die in detonations so vast we had to invent new words, supernovae. When a massive star runs out of fuel, its core caves in, and in that final collapse it rebounds with such violence that the entire outer shell is blasted into space. For a brief moment, a single dying star can outshine an entire galaxy. It is in those explosions that the universe writes its chemistry. The iron in your blood, the calcium in your teeth, the gold in wedding rings, all of it forged in stellar cores and scattered by stellar deaths. Without explosions, there is no you, no me, no Earth. The cosmos creates through violence. Even stranger are the rarer events, gamma-ray bursts, which flicker like cosmic flashbulbs when stars collapse into black holes or when neutron stars collide. In seconds, they unleash more energy than our sun will emit in its entire lifetime. To be within a few light years of one would be extinction. To watch from afar is to glimpse the rawest power nature allows. Against this backdrop, nuclear bombs are not inventions but imitations, are small-scale rehearsals of what the universe has always done. The difference is intent. Stars don't choose to explode, they obey physics. We, on the other hand, lit our own suns in war. That duality, the same physics, bent toward different ends, lingers like a shadow. Nuclear energy has always balanced between two futures, the sword and the torch, apocalypse and exploration. One path leads to scorched cities and dead satellites. The other points to starships leaping between worlds, powered by the same reactions that light the galaxies. So when you think about Orion, don't just see a mad Cold War dream. See it as part of a continuum. From the sun that warms us to the supernova that seeded us to the bombs that threaten us, the story is one. Energy, locked in matter, waiting to be set free. The question is never whether it will be released. The question is, what story do we write with it? And here's where the story bends toward philosophy. Because in chasing the atom's fire, we've stumbled onto something larger, the paradox of destruction and creation. For humans, nuclear explosions are almost synonymous with apocalypse. Mushroom clouds, shadows burned into walls, cities erased in seconds. They are the stuff of nightmares and deterrents, the final card in the game of war. But look at the universe, and explosions aren't endings, they're beginnings. A supernova doesn't just obliterate a star, it enriches the galaxy with the elements needed for planets, oceans, and DNA. A gamma-ray burst can sterilize unlucky worlds, but from its ashes, new systems form. Even the Big Bang itself, the ultimate explosion, wasn't destruction at all. It was creation. Space, time, and everything we know burst forth from that singular event. So what does that make us? Wielders of tiny imitations of cosmic fire. When we detonate a bomb, we see only the ruin. But the physics itself is neutral. It's the same process that lights the sun, the same conversion of mass to energy that built the chemistry of life. The question isn't whether nuclear fire is good or evil. The question is what we decide to do with it. History shows both faces. Hiroshima and Nagasaki, unspeakable loss, cities turned to cinders, survivors carrying scars for generations, but also nuclear medicine, using isotopes to fight cancer. Nuclear power plants, flawed but cleaner than burning coal, lighting cities without choking skies. Scientists still dream of nuclear fusion reactors, tiny suns on Earth, offering endless energy with barely any waste. The same physics, but bent in a different direction. Even space itself is a reminder. The Carrington event of 1859 showed us how a natural cosmic EMP could set telegraphs aflame. Starfish Prime reminded us that our own weapons can echo the sun's fury, creating auroras and knocking out power from half a world away. Destruction and creation, two sides of the same equation, always bound together. And so, we return to the midnight question. If you set off a nuke in space, what happens? The answer isn't just physics, it's a mirror. It shows us the raw truth of the universe, that explosions shape everything, and it shows us the raw truth of ourselves, that what we do with that power defines our story. Because if the cosmos writes with explosions, then so do we. The only difference is that we get to choose what we write next. So maybe the real lesson of nuclear fire isn't just about weapons or technology. Maybe it's about perspective, how we, a species born from stardust, decide to use the very forces that once forged us. Think about it. Without ancient stellar explosions, there would be no heavy elements, no rocky earth, no iron in our blood. The same physics that terrifies us in mushroom clouds is the physics that made it possible for your heart to beat. In that sense, every nuclear detonation is a reminder, grim or awe-inspiring, of our origins. On Earth, we see the bomb as an ending, but in space, stripped of its thunder and smoke, it becomes something else, a flash, a ripple, a whisper of the same processes that power galaxies. The violence looks different in the void, quieter, purer, almost humbling. It reminds us how small our greatest weapons really are compared to the engines of the cosmos. That's why the treaties mattered. The Partial Test Ban Treaty, 1963, the Outer Space Treaty, 1967. They weren't just about restraint, they were about recognition. A recognition that space isn't ours to scorch, that filling Earth's orbit with radiation belts could poison not just our rivals, but ourselves. In that moment, humanity admitted something rare. Some doors are better left unopened, and yet the dream lingers. Not of blowing things up, but of harnessing the atom's fire for journeys instead of wars. Nuclear propulsion, nuclear power for colonies, even the promise of controlled fusion. These are echoes of Orion, stripped of its recklessness. They are our attempt to write a different story with the same ink. Because that's the choice we always face with energy. Fire once burned forests and villages, but it also cooked food and forged tools. Electricity shocked, but it also lit cities. Nuclear fire can flatten worlds, or launch us to others. The physics won't decide, we will. So if you ever find yourself staring at an image of a mushroom cloud, or at the auroras shimmering over the poles, remember, they are both faces of the same coin. One is terror, the other is wonder, and in the end the coin is in our hands.